last talk is given by Dr. Chih-Wei from the National Center for Chih-Wei Science. The title of the talk is Calculation for Ricci flow based on the Ricci flow.
Thanks to the organizers for inviting me to give a talk here, and I think it's a very good opportunity for me to introduce my work to all of you. And I also wish that we can have more cooperations, maybe if you are interested in my work. Okay. So today I will talk about the curvature estimate along the Ricci flow. So in fact, there are several motivations of my work. One is from my earlier work. Because long time ago, I focused on the curvature decay of expanding soliton. And at that time, I have some estimate problem. I cannot solve it. So I turn my, how to say that? I try to study the general Ricci flow and try to find some generic property, not focus on the expanding soliton itself. And eventually, I derive this estimate for general Ricci flow. And the components of the Ricci flow is another motivation. Okay, so after I tell you the motivation, I will state my theorem. And the theorem has several versions. A standard one, a compact one, a non-compact one, and a refined one. Anyway, I will give you a standard version and the proof because it will be easier. If you look at the complicated refined version, then you will lose your direction. Okay. And also this result can be applied to study the Taming problem of the Ricci flow. For Taming problem, I mean that just as mentioned in Professor Tam's talk, if Ricci flow satisfies a curvature bound like this, then I say that the curvature operator is K-tamed. Okay, so this will be an application of my theorem. The third topic is, in fact, my theorem can be seen as an alternative for Moses iteration. I will talk about this later. And because the proof of my theorem is more geometrical, not an analytical approach. So it provides an analog to the Moses iteration, which is purely PD approach. And I will tell you some further investigation, which I'm focused now. Okay, so this is the first, one of my motivation is a convergence of Riemannian manifolds, and especially convergence of Ricci flows. I think almost all the audience here, you are familiar with this. If we have a sequence of Riemannian manifolds, which has a sectional curvature bound and volume low bound at one point, then we can have subsequent converging C1 alpha topology. And also, if we change a sectional curvature bound into a Ricci bound only, then we need a stronger bound. We need a bound stronger than the volume low bound. Here we can put an injectivity radius low bound at each point. Then we can also get a C1 alpha subconvergence, and the proof can be found in, for example, in Anderson's paper in the 90s, where he showed that if we have Ricci bound and injectivity radius low bound, then we can bound the harmonic radius. And under the harmonic radius, we can argue the convergence of Riemannian metric. Okay. So to the Ricci flow, we have Hamilton's companion theorem, which says that if a curvature is bounded and volume has a low bound, then we have a C-infinity convergence, subsequence converges in C-infinity topology. And here we have a C-infinity. The regularity comes from the Schiss estimate, because once you have a curvature bound, then you can bound all the derivative of the Riemannian curvature operator. So in this case, you get you get bounds of all derivatives of curvature operator. So the regularity can be improved into any order you want. So we get a C-infinity convergence. So a natural question is, if we replace the curvature operator condition by a Ricci curvature, and we replace this by injectivity radius, then can we prove the Hamilton's competence theorem? And I mean that if you have a Ricci and injectivity radius bound, can you get C-infinity bound? We should note that the C-infinity comes from the bound of Riemannian curvature. So if you don't have any information on the curvature operator, then how can you derive a bound for higher order, right? So eventually we see that this is true. If you have a Ricci bound and injectivity radius low bound, then you can get a C-infinity convergence. So this is one of my one corollary of my main theorem. So the main theorem is given some constants here, delta and eta, and the dimension n is at least 2, then there exists two constants, alpha and c, such that for any Ricci flow which is smooth and defined up to a definite time interval, if a time is too small, then I cannot improve the metric, right? Just like a Schiss estimate, you need a definite surviving time for the flow to improve the curvature bound. Okay, so there is a low bound of capital T. Then in this case, if you have a Ricci bound and injectivity radius low bound, I write it in a scaling invariant form. Okay, then you will have a bound on the gradient of Ricci, the derivative of Ricci curvature. So it's a kind of a Schiss estimate of Ricci curvature. And once you have this, then you can prove that curvature operator is also bounded, and the bound is very clearly depend on the bound of Ricci curvature, and this is a capital T, and the order of smaller t is -1. Okay, so it's the one I just named it by 1/10. Okay, so under this condition, we can prove that the curvature operator is 1/10 along this flow. So in particular, we get the corollary I just mentioned, the Hamilton competence theorem, with assumptions replaced by Ricci and injectivity radius. And I should mention that, in fact, this corollary has been implicitly proved by Dai Xianze, Wei Guofang, and Ye Rugang, but they didn't write it in this form. They study another problem, and they derive some existence result of closed Ricci flow. But anyway, from their proof, you can just write down it carefully and check it. You can see that this is true from their result. Okay. Okay, so I will show you the proof of a main theorem, and later I will tell you can we replace this by weaker assumptions. And some are very interesting if you can replace it by some very weak assumption. Okay. Anyway, let's prove the simple version. This one. Okay. So to prove this, we use harmonic coordinates. Okay, so harmonic coordinate means that you can have locally for any point on a Riemannian manifold, locally you can choose a good coordinate. And a special one is called harmonic coordinate. It means that each coordinate function is a harmonic function with respect to the Laplacian given by Gij, and Gij is the coefficient of a metric expressed by the harmonic coordinate. Anyway, okay. So you can derive that under this coordinate. If you compute the Laplace of Riemannian metric, then it will equal to minus 2 Ricci plus some low order term. Ricci is a second derivative of metric, right? So and this involves only G and the first derivative of G. Okay, this is a combination of G and partial G and determine something like that. Anyway, it's a low order term. So by Schroeder's estimate, we have this. If a right hand side is bounded by C0 alpha, then the left hand side is the C2 alpha norm of G can be bounded by this. Okay, so it means that if we can prove that Ricci is bounded and the derivative of Ricci is bounded, then under the harmonic coordinate, we know that the C2 alpha norm of G is bounded because harmonic coordinate has C1 alpha control of a metric. So under harmonic coordinate, by definition, this is controlled. And what we want to do is we want to control the derivative of Ricci so that this is bounded. And then we can have a C2 alpha bound of G. It means that the curvature operator has a C0 alpha norm, C0 alpha bound. Okay. And okay, as I mentioned before, Anderson proved that if you have a Ricci bound and injective radius bound, then you can have a definite size of harmonic coordinate. So you can obtain this control on a definite size of a region of definite size. Okay. So what we prove is this: if Ricci is bounded by K and injective radius is bounded by delta over square root of K, and T has a low bound, then the derivative of Ricci can be bound by this. And the proof is by contradiction. We assume that if this is not true, then suppose no such alpha exists, then we can find a sequence of Ricci flow. Because I want to prove this estimate for all Ricci flows, so we need to assume that there is a sequence of Ricci flow and with different point pk, with different alpha k, and with different capital K and capital T. And everything is depend on the small k, depend on the sequence. Okay, so we have a sequence of Ricci flow, and each sequence, each Ricci flow has a sequence, has a point xk tk, such that the derivative of Ricci is larger than this. So maybe we say equals alpha k, with alpha k goes to infinity, and the idea is, okay, we rescale this. We scale the matrix around this point, pk. Then, so that the derivative of Ricci becomes 1 for every k. Then, because Ricci curvature is bounded by k, right? So if the derivative of Ricci blows up faster than k to the power 3 over 2, then if we rescale it back, then Ricci will go to 0, right? Because Ricci is much smaller compared to its derivative. Okay. Remember that we want to prove that the derivative can be controlled by Ricci itself, right? So if this is not true, it means that the derivative blows up very fast, faster than Ricci curvature. So if we rescale back, so that the derivative goes to 1, becomes 1, then the Ricci will tends to 0. Okay, so if the convergence, if we can prove the convergence, then we get a contradiction because in the limit you have a Ricci flat manifold, but the derivative is 1 at some point, right? So what we want to do is how to justify the convergence. Okay, if you have this point, how can you take a convergence of a matrix? So there's a important lemma. This is similar to the Perelman's point picking lemma. In a singular analysis of Ricci flow, Perelman has the same problem, right? You have a point and with curvature blow up. How can you rescale the matrix? You need a parabolic neighborhood near the point. If you have a point and you want to do the rescaling and blow up, you need to find a space-time parabolic neighborhood with good properties, so that after rescaling, this parabolic neighborhood has good control. At least the curvature, after rescaling, the curvature here should be bounded, so that you can take a convergence subsequence. Okay. So we need a point picking lemma which says that near the point pk you can find a parabolic neighborhood, so that in this neighborhood all the derivative of Ricci can be bounded by 8 times the derivative of Ricci at the point pk. Okay, at each point you need to find a parabolic neighborhood. And here you have gradient Ricci. I denoted by qk. Okay, and we want to find a point, a good point to blow up. And this point, we hope that each pk has a parabolic neighborhood with this less than 8 times this. So it's exactly the same situation where Perelman encountered in his analysis of singularity. So the point picking lemma is here. The proof is the same to Perelman's one. Okay, just argue in a region. Okay, so if you consider a Riemann manifold here and the Ricci flow here, and if you have some point which has a very large whose derivative of Ricci is very large here, then you can find another point just nearby. Not always. You can find another point somewhere. And this point has a beta property, which means that it has a nice parabolic region, so that you can blow up along this point. Okay, so the proof is if you choose a point here and you cannot find a parabolic neighborhood, it means that there is a bad point here with number of Ricci larger than 8 times the number of Ricci here. So the Q here will be larger than 8 times QK, right? And this point, if you consider his parabolic neighborhood, then if this point is not your candidate, does not satisfy the bound of Ricci derivative of Ricci curvature, then you can find another bad point. And in this case, if you argue inductively, then eventually you will get a lot of a sequence of points with qk goes to infinity, or it stops somewhere with a good neighborhood. Okay. So if qk goes to infinity, it means that your matrix is not complete. So this is impossible. So eventually you will stop somewhere. So you find your P bar. Okay. Okay, so let's proceed to finish the proof. Suppose there is no such alpha, then you can have a sequence of points which has a very large QK. Then by point picking lemma, you have a region. And in this region, your number of reaches is bounded by 8 times QK. So you can rescale the matrix by Q to the power 2/3. Then you see that the gradient reach at PK equal to 1. And the gradient reach on this neighborhood is less than 8. And the Ricci curvature goes to 0. And injective radius is larger than this is our assumption, right? Times Q to the power 1/3. So this will goes to infinity because Q to the power 1/3 is this one, the square root of this. Then you can see that square root of K canceled out, and alpha K goes to infinity. And TK, smaller TK is, small TK is smaller than the capital T, right? So this will goes to infinity. So if once you have this, then you can have a harmonic radius, and under the harmonic coordinate, and you have this control, so you can see that the curvature operator is uniformly bounded. Okay, and by Schi's estimate, you know all the higher derivative of reaches of Rm is bounded. So you have a smooth convergence. So smooth convergence will tell you that in the limit, this is 1 and reach is 0. So this is a contradiction. Okay, so we can observe that here, to take a limit of such a sequence, we don't really need an infinite injective radius. We only need a low bound of this. So if we replace the assumption of injective radius, this is our assumption delta over square root of K. And if we replace it by something else, for example, we replace it by delta times square root of T, then it also works. You can cancel out the square root of T here, and KT is larger than eta. By our assumption, T is larger than eta over K. So KT has a definite low bound. So we get this another version of our theorem. The previous one, we assume that injective radius is larger than delta over square root of K. This is a definite constant. But if we replace it by only square root of T, it means that your injective radius is allowed to be 0 at the initial time. It means that you don't really need the injectivity low bound of initial manifold. You can prove this theorem. You can prove the one-tenth property without knowing the injectivity radius information at the initial time. Okay, so and also this theorem holds locally. I change everything into a local ball with a radius depend on square root of T. It's also a scaling invariant size. Okay. So an even strong version is if you look at the proof carefully, you will see that here is square root of T because of you are 1 over T here. So if you replace T by another function H, then you can put H here. So it means that your injectivity radius could be anything. I mean, because you have Ricci flow up to time equal capital T, then you can just look at the injectivity radius and you find a small function to be a low bound of an injectivity radius. So this condition is always hold if you can find a smaller h to put it in under the injectivity radius. So if an injectivity radius in the beginning is the quantity is larger than 0, then it moves like this. Then you can always find the h here. So in this case, you can get a curvature bound which looks like this. H, yeah. So it is not 1/10 because this is not t, but you still get some information, maybe 2/10 or 3/10, depends on what h you choose. And this h is very arbitrary. In fact, you can take any function which is concave down, in fact, or you can take a t square or something. Anyway, it's quite arbitrary. Okay, so in fact, although our proof, our theorem involves injectivity radius, but this low bound is very easy to achieve. Yeah, but it's not a priori assumption. You still need to look at the flow for all time, and then you can find the injectivity radius low bound. So you cannot just look at the initial manifold and solve anything. Okay. So a second remark is, in fact, the injectivity radius can be replaced by harmonic radius. In my proof, I only use it to ensure there is a harmonic radius. So I think for some of you, harmonic radius is much better than injectivity radius. Yeah. Because we don't really know how to derive an injectivity radius estimate along Ricci flow. Okay, but harmonic radius is better. It's easier to derive. For example, you have volume control. If your volume is almost Euclidean, then you have a harmonic radius. Right? You don't really need injectivity radius. Okay, so. There's one thing important here. I should mention the h is any function less than t and positive. So as I said before, injectivity radius at the initial time is not important, right? Because in the initial time this is 0. So it means that we have a chance to study singular initial manifold, right? But this is not true up to now. Okay, here I assume the flow is smooth, and at least this is because when we prove the point picking lemma, we need that this is finite for all t up to the from 0 to capital T. So in fact, the proof holds for Ricci flow at least C3. I mean, we cannot use this theorem to study Ricci flow with singular initial manifold. But later I will go back to this issue. Okay, so one corollary is this. So apply our theorem, we can see that there exists a universal constant which depends only on n. It does not depend on the Ricci flow itself. So for any Ricci flow which is smooth, then you can have a 1/10 property up to some time, and this time depends on the Ricci curvature bound and the injectivity radius low bound. Okay, so it looks like this. You have a 1/10 curvature operator up to some time tau, and tau is mainly depend on the injective radius. So the red curve is the injective radius. This is the first time the injective radius break square root of t and goes downward. So this is the first time. This is tau here. Okay. But it might not control up to tau, because if your Ricci is very large, so it will change the upper bound before t goes to tau. Anyway, we get a universal constant, and the time depends only on the injective radius and the Ricci curvature. There are several results. For example, I mentioned before the work of Dai Xianze and Wei Guofang and Ye Rugang. They prove that there is a constant depend on N and the Ricci and the injective radius, so that this can be controlled. Yeah, so we just make clear the dependence of the constant. Okay, so the third part of my talk is about the Moser iteration, the comparison between Moser iteration and my argument here using Perelman's point-picking lemma. So let me recall the Moser iteration. This is a version given by Dan Young in his 92 paper. And if you have a function satisfies this equation inequality, then if you have an integral bound of B for all t, then you have a pointwise bound of U. Okay, and this bound depends on the LP bound of initial value of U. This is Moser's iteration, and for example, for Ricci flow, we have this inequality for curvature operator. So it looks like this, right? And you just take B to be the curvature operator. Then it says that if a curvature operator has a special bound, integral bound for all t, then it is bounded pointwise. Okay, and in fact, I think all of the authors are here, Coscio and Montiano and Wang. They prove that along the Ricci flow, if you have a Ricci bound and the initial curvature bound, then the LP bound of curvature operator holds for all t. Then you can use Moser's iteration to get the pointwise bound. But the bound is explicit, but it depends on a lot of parameters. I mean, for example, we don't know is 1/10 or not. We don't know how it depends on t. It involves some exponential term, something like that. And okay, so compare our method. In fact, if you change the condition here, initial curvature bound, you replace it by the injective radius low bound, then by their approach, we can show that the curvature has the same upper bound. Okay. Okay. So this is compared to our theorem. Our theorem says that if you have a Ricci bound and you have injective radius bound by something for all t larger than 0, then you have a curvature bound. And if we use the approach of Coscio, Montiano, and Wang, and then you can see that this can be replaced by the initial injective radius. So it's quite interesting. These two approaches involve different information. And so I just think, okay, of course, if you look at if you compare these two estimates, there are different advantages in both sides. The one is this one only involves the initial data. It's better, right? Better than you involve all the information along the flow. But the disadvantage is the bound is not so clear, because in our theorem, the bound is much clearer. In particular, if Ricci is very small, then the curvature operator is also very small. And this is useful in my situation when I study expanding soliton. Okay, but it's not so perfect. In fact, if k is small, then the capital T must be large. Okay, so it's not really very useful, because when you want to when we want to show that when for example you have some Ricci decay and you want to prove that the curvature operator decay at the same rate, in this case you need a very large T. It means that you can study it on an ancient solution, something like that. You cannot prove it for expanding soliton. Okay. So let's go back to this case, which I just mentioned before. It seems that it's possible to apply our approaches to study Ricci flow with singular initial manifold. And in fact, if you look at the proof carefully, you will see that you can replace the curvature Ricci bound by this, by LP bound for some p larger than n. This is quite crucial. In fact, roughly speaking, we hope p is not so large. So p larger than n is not so good, but still can be used. Okay, in some cases. Okay, so in our proof, if you just rewrite some sentence, then you have this. I write it as a conjecture, not theorem, because I just finished this last week. So I'm not quite sure. Okay, so we can replace the Ricci pointwise bound by an integral bound, and a Ricci low bound, which is comparable to the harmonic radius. So this one is also a very bound very easy to be achieved. Okay. It's a bound like this. Okay, so in this case, if this is true, then we can use it to study the manifold with initial condition. This, I mean, the initial manifold could be non-smooth, and for example, you have initial manifold with log singular points. It means that you have some singular points, and the Ricci blows up like log R. Then in this case, you can use the theorem, and you get that your Ricci flow makes the curvature operator 1/10. Okay, so I didn't finish the investigation here, so maybe I can improve something so that it looks more clear. Now it's not. Now it looks ugly. So okay. So this is my. I think I stop here. Thank you. Yeah, that's a problem. In fact, if you can prove this p larger than n over 2, then this is a very significant result. I mean, it's possible, but it's hard. Yeah.
Why is you need a n greater than p greater than n, not a half n?
Yeah, that is because you have a Sobolev embedding theorem, which tells you that if p, you want to embed this into C1 alpha, but this is true only for p larger than n. If p is smaller than n, say between n over 2 and n, then you can only get this, something like this. So you lose some regularity of a matrix. So you cannot prove harmonic radius low bound or yeah. I mean that the theorem depend. The assumption of a theorem is LP bound. So if you have a good harmonic coordinate, then you can improve the bound by shorter estimate, then you get a W2P bound. But W2P bound is not good enough. In fact, you want to use a C1 alpha bound, and in this case, you need to. I need the assumption P larger than n. So.
You assume you take the
Yeah.
condition. Any condition require a non-corrective, then prove your estimate.
Yeah, I tried, but the non-collapsing. If we have a Ricci non-collapsing, then I can do this. But non-collapsing means that you have a curvature control and you have a volume, right? But what I want to prove is a curvature bound. So I cannot assume that okay you are non-collapsing and I cannot use it because that is what I want to prove. But if I have some Ricci non-collapsing assumption which ensures that you have a Ricci bound and you have a volume low bound, then this could be used. But it's an artificial definition. Right?
Okay, but you assume the initial condition, for example, curvature have a scalability part to apply non-curvature. In certain cases, you just only assume the scalability part.
I don't know. Yeah.